Okay, we're still talking in chapter 15, bulk deformation processes. And chapter 15 as a bulk deformation, we have four processes as we described earlier: rolling, forging operation, extrusion, and finally wire and bar drawing. Today, already rolling, forging, extrusion already finished. Now or today, we're going to talk about wire and bar drawing. This is a rolling, this is the forging process, this is the extrusion. Today is wire and bar drawing. We're going to start talking about wire and bar drawing. Okay, this is a wire and bar drawing. In a wire and bar drawing, we pull, not push. There are no pressure here. We are not applying pressure. In extrusion, we're applying pressure here. We push the material, applying pressure, push the material to exit from the die opening with the same shape. Here, this is a wire drawing is different from extrusion actually. There are no pressure but tensile stress. We're pulling the material. We're pulling the material here, so we apply tensile stress to pull the material to draw the wire. So it is cylindrical shape and finally also cylindrical shape. Because it is a wire, so we pull the wire to shape the wire. So this is a wire and bar drawing. Here is this is a wire and bar drawing. This is we're pulling. This is a die here. This is a die to pull the wire. So here we pull the wire. We have whatever we call area reduction. R is the area reduction, which is the AO minus AF. AO area initially, AF area finally. AO minus AF divided by AO. We call it is the area reduction or reduction with draft equal to DO minus DF. DO minus DF. This is a draft. Now, as I told you here in the wire and bar drawing, we're pulling the material. We're not applying pressure, but pulling the material from here. So we apply now tensile. Tensile stress, we apply tensile stress to pull the material. And even actually, we apply tensile stress here to pull the material. We're applying tensile stress here to pull the material. However, you can see compression also is there because when you apply tensile stress, material will flow, you squeeze the material in a die. So not only tensile here and compression in the opposite direction or in the other direction. I mean that this is a second compression. Then here squeezing the material. So it is actually not only tensile but tensile and compressive stress together. Then we have both actually in applying in wire and bar drawing. We have whatever we call wire and bar. Wire and bar. But let me before that, let me show you a nice video to describe this process. Right. It's coming. Yep. This is wire and bar drawing. You can see. Right. This is a wire drawing. This is a wire that we would like to draw. It is circular shape. This is a die. You can see that. We're going to reduce the size by using the die. A first step to pointing, to make pointing. Pointing means to make this shape. Pointing to be able to enter the die, right? This is the die you put in the die. Then this is the other side because of pointing. This is the other side. Actually, not by hand. He just tried to show, but not by hand. It's not possible to do this by hand. Then you cannot draw by hand actually. It is just to show. And then here, this is the pulley, rotating pulley. This is the wire and rotating pulley. So wire here, wire drawing. This is a wire drawing. Here you reduce here. Probably it could be one cycle, could be series of drawing. Could be series, not only one. It could be one, could be different. This one is rotating here to pull. We're rotating here this drum. We're rotating on a drum and we're rotating the drum to pull it. Then we apply tensile now. This is the tensile stress. There are no, the other end is free. So we just apply tensile stress to reduce. Different application actually, wire, spring, this clip. and many other products can be produced from the wire drawing. Right. So this is a wire drawing. In general, this is a wire drawing. Right. Get back to the slides. So this is a wire drawing. When you talk about wire drawing, we have actually not only wire and bar. We said that bar and wire. What is the difference between bar and wire? Is there any difference? The bar is a large diameter. When the diameter is big, we call it is a bar drawing. Wire is a small diameter, down 0.03 millimeter. Small one is a wire. This is a wire drawing. This is a bar drawing. Bar drawing. Bar, the only different bar is big diameter. Wire small diameter. Because wire small diameter, we can wound it in a rotating drum. So wire usually wound it in a rotating drum. However, bar difficult because bar is big diameter. Then it's very difficult to. It is, as you can see here, is a straight line. You pull as a straight. You cannot just make it round like whatever in a wire. This is a big difference, but mechanism is same. There are here, if you look, the mechanism is same here. This is a die, reduction die here, also reduction die. Both have same reduction die, but the only difference here, this one small diameter, this one big diameter, but mechanism is same. Usually wire and bar drawing cold working or performed at cold working, right? And usually round cross section. Here round cross section and here round cross section. And the product is a wire, a rod, clip, whatever. Several product can be produced from wire and bar drawing. This is the drawing equipment. When you come to the drawing equipment, start first with a single draft bar drawing. This is a bar drawing. Bar drawing, as I told you, it is a big diameter. Big diameter is this is the equipment actually. Equipment. This is the equipment in a bar drawing. So in the bar drawing, as I told you, it's a big diameter. This is a mechanism. This is a die. I mean, this is a die reduction to reduce the diameter, as you can see here. Single draft operation. This one single draft operation. Stock is pulled through here. We're pulling. This is a hydraulic cylinder. This is a hydraulic cylinder, and this is whatever we call carriage to hold the parts. This is a two part here. We're pulling two part together. This is a carriage to hold the two part here, and then this is a hydraulic system to pull it. So we pull here. This is a single draft operation to pull the bar through one die opening here to reduce. Because the beginning stock is a large in diameter, it is in a form of straight cylinder, as you can see here. A straight cylinder, and this actually limits the size. So how big, how long? Very limited, because here you can see that stroke is identified by the stroke of the cylinder. So it will be very limited. The size will be very limited in this case. This is the first one, or the equipment being used in the bar drawing. Next is the equipment to be used in the wire drawing. In a wire drawing, situation is better. Why? Situation is because our diameter is small, we can round it in a rotating drum. So this one we say this is several hundred feet because you rotate actually you rotate, so unlimited length, not as a previous limited with a cylinder length. This is unlimited length. This is, we can say this is several hundred feet of wire or 100 millimeter or 100 meter of the wire pass through a series of dots. Could be one, could be single, could be series, could be one, two, three. It depends on what is the final size and what is the initial size. So this is the initial size. You here make a reduction and then another reduction and so on. You get a final size at the end of the process. Everyone is a die. You can see this one, this one. So everyone is a single die. This is a continuous drawing. So every rotating the drum here is to apply tensile in the periphery. So this one apply tensile here and feed to this one. This one apply tensile here. So always tensile, always tensile. Right. Okay, let me show you this one. Right. Just a second. This is drawing process. This is die. This is a die reduction die. He's coming and here die here. You can see this one applying tensile stress here. It's pulling. This one rotating pulling. So here this one rotating pulling apply tensile stress here. We have tensile stress here. This is the die. This is the oiling system to oil. There are a oiling system here to oil. This one rotating to apply, you see it is rotating. This is the rotating drum. We rotate the wire on the rotating drum. So rotating drum to apply tensile stress here. We apply tensile stress here. And this is the main actually. This is the main wire system. This is the main wire system we bring from here and make series of reduction. So finally you can see that series of reduction to reach to the desired whatever dimension needed. So first stage, second stage, and so on. Then you can obtain the desired shape at the end of the process. Okay, so this is a wire. So this is a wire diameter. You make a small reduction, small reduction, small reduction, but finally you get the desired dimension at the end of the process. Okay, preparation. When you do preparation, what preparation you need to do for wire and bar drawing? First one, you need to clean the part and you need to do annealing. You need to clean and annealing. You get the initial one, you do cleaning for the first time. You do chemical annealing to make it ready, and then chemical cleaning to make it ready, and then you do annealing. Annealing, what is annealing? Annealing, you actually heating this one up to certain temperature and you leave it to cool down and slowly, no quenching, you just leave it to cool down slowly, then make material soft. This process, annealing process, make material soft, softening the material. So you do annealing as a first step, preparing the material for the next step, which is wire drawing. Also in the preparation you need to do pointing. This whatever we call pointing. Pointing is to make point here. Pointing. This pointing is needed to able to put this one in a die. So pointing, you need to do point. This is a preparation. And next we have either dry drawing or wet drawing. Dry drawing. And then we have also whatever we call wet drawing. Wet drawing actually is easy. This is oil. As you see, there are an oiling system, and then you apply oil in drawing to reduce the friction while you do drawing and so on. This is a wet. Dry, you put this whatever we call dry lubricant. Dry not meaning nothing. There are dry lubricant. Dry lubricant here they call it soup. Soup, it's like paste they put in the surface before you do the drawing process. And this one usually, this one dry or powder or soup being used in case of high temperature. Air cold working, you just simply put oil. But when you have temperature, if you heat the material, usually in the bar drawing, if you heat the material, then probably oil is not function. Then you put soup, which is the powder, and then you make it paste and you put in the surface, coat in the surface in somehow, and then you do using this one. So this is whatever dry drawing. This is a wet drawing to reduce the friction, actually, mainly to reduce the friction. This is a die, actually. This is a die. This is the feature of the die is the entry region. This whatever we call entry region. This whatever we call approach region. And then here we have this is the bearing area, and then finally back relief area. This is a four feature in a die. Entry. Here we added lubrication. This is mainly good for to add the lubrication to reduce the friction later. Approach here, material will deform. Material will deform. This is a cone shape. Oh, drawing happen here from here to here. This is a contact area, and drawing happen here. Bearing here. This is the final size. Determine the final size. This is the final size of the wire. Relief is needed to not destroy the drone machine. I mean to keep the die away from the surface. This is let me say this is a drone surface. For example, this is a drone surface, as you can see. I would like to keep the die away from that. So this is a relief. So relief is to exit, able to exit freely without in contact with the die. This is whatever we call relief or clearance. A die could be made of solid, made as solid material, or made of insert. You can have a holder and insert. This is a holder and insert. Die is being made as an insert from hard material like tungsten carbide. So this is HSS, for example, high speed HSS or tool steel or die steel or whatever to be used to manufacturing the die. So it's made of solid, or it could be made as this is casting steel and this is the tungsten carbide. Tungsten carbide is very hard material, so make it as insert to put in the holder. This is the holder, and there's the idea to use whatever we call very hard insert like tungsten carbide insert is drawing harder material. This usually needed when you draw harder material. When you draw harder material. Angle, die angle, when you talk about the die angle, this is a die angle actually. This is a die angle here. This is a die angle alpha. Die angle actually, they find that experimentally, they do some investigation. They find that whenever the reduction percent increase, die angle should be increased. So this is the die angle value. This is a stress. So whenever reduction increase, this is a higher reduction, this is a lower reduction. At lower reduction, to get the best condition, to get the lowest stress possible, at lower reduction, usually die angle is small. But when a reduction increase, whenever reduction increase, you can see that this is the optimum die angle in every case. You can see that the die angle, optimum die angle increase whenever reduction increase. So for high reduction, angle usually big. So usually die angle between 6 to 15. In case of low reduction, it is usually 6. For higher reduction, usually up to 15 degree. Usually. Right, this is mechanics of rod and wire and bar drawing. Stress here, we apply stress. As I told you, we're pulling the workpiece. We're pulling the workpiece here to deform the workpiece. So this is a wire drawing. So stress usually equal to Y bar flow. We need Y bar flow. Y bar flow because here it's fixed process. We start with certain diameter. You reach to it in once. There are no steps in the middle. There are no steps to say. In two cases, if you have a steps mean you apply to get certain value and then you apply, you get this. Whenever you mean strain is variable. In case of strain variable, then you have to use Y flow. But in case of strain fixed, then you have to use Y bar. Here strain fixed, Y fixed. Because you start with certain diameter, you end with certain diameter. Finish. Strain is finished. Strain is fixed in a process. The strain equal to, or true strain definitely ln AO divided by AF. Ln AO divided by AF. So in all process, only one strain. In all process, we have only one strain, which is equal to ln AO divided by AF. In this case, stress equal to Y bar flow epsilon. Y bar flow epsilon. This is the stress here required to draw the material. Y bar flow epsilon. Y bar flow equal to K epsilon N divided by N plus 1, and epsilon here equal to ln AO divided by F, or ln 1 divided by 1 minus R, where R is area reduction, AO minus AF divided by AO. Definitely the force, if you would like to get the force is here. Be careful here. Force is here. This is a force. So force is here. When you said force equal to what? Equal to sigma drawing multiplied by AF. sigma drawing multiplied by AF. Then y by flow AF ln, or is it epsilon ln AO divided by AF? So this is a force. So this is a sigma drawing and this is F. This is the ideal case. No friction and no ideal deformation, homogeneous deformation and no friction. This case, I mean, it will be ideally no friction. I didn't consider here, or they didn't consider now, friction. They didn't consider any homogeneous deformation. In this case, this is a sigma, this is a force. It is very simple. This equation is very simple, right? You call it ideal case. So this is ideal case, no redundant deformation or no inhomogeneous deformation and no friction in the work. Somebody said that, is it okay, this one? Can we use this ideal one? I said, this is very rough. We were going to modify it. Actually, people doing like that. Start with a simple case. Start with a simple case, ideal case, no inhomogeneous deformation, no friction, and just make it simply like simple tensile test equal y flow multiplied by epsilon as a simple tensile test, and then modify equation to deal with the actual case when friction applied and non-homogeneous deformation applied. When it will happen step by step, let's just move forward and see. We're going to modify the equation, or they already modified the equation to deal with the friction and non-homogeneous deformation. So this is the ideal case. Ideal case, stress in ideal case, force in ideal case. This is the ideal case. And also in ideal case, this is that what is a maximum reduction as an ideal case. What is a maximum reduction could be done in this process in an ideal case. The maximum reduction happen, they said that the maximum reduction happen in case material is fully plastic. You know, material is fully plastic with n equal to 0 in this case. Material is fully plastic when n equal to 0. NH is the slope of the line in stress strain diagram. So n is equal to 0. This is fully plastic material. It means that materials, there are no yield. When you reach yield stress, material will plastically deform immediately, and below yield stress, there are no any deformations. There are no any deformation. When you reach yield, then material will deform plastically permanently without any elastic recovery. This is very theoretical. We don't have this. We don't have this. This is very theoretically, right? We usually have elastic plastic material. The case elastic plastic material. In this case, n equal to 0, when you apply n equal to 0, you can find that yield stress equal to K equal to Y flow equal to Y bar flow. In this case, here, in this case, usually sigma D equal to Y bar flow equal to K, meaning you can see that ln AO divided by AF equal to 1. This is very theoretical case. As I told you, this is very theoretical case. Then ln AO divided by F equal to 1. Then AO divided by AF equal to E. When you apply in a reduction, you can say that AO minus AF divided by AO, then AO, then 1 divided by E, then you get 63%. This 63% is the ideal case in deformation. Ideal case in deformation. No considering here elasticity of the material, no considering friction, no considering redundant or non-homogeneous deformation. So it is 63. Actually, this is very high. This is very high reduction. Actually, this is very theoretical. Not consider, as I told you here, not consider all this variable. However, actually in industry, they find that in practical, they find that a reduction could reach up to 50% in single draft. Reduction could reach up to 50% in single draft. Single draft means one stroke, one time, right? But it could be maximum 30% reduction in case multiple draft, mean you do one reduction and then you do another reduction and then you do another reduction and then you maximum get 30% in every. This is industrial practical reduction value in industry. Now, need to modify the equation as I told you. Equation was very theoretical, not considering friction, not considering redundant or inhomogeneous deformation. Then this is a part they added to the equation. So equation was y bar flow sigma drawing equal to ideally ideal equation equal to sigma drawing equal to y bar flow ln AO divided by F. This is the equation. It was like this initially, which is in ideal case, and no friction consider and no inhomogeneous deformation consider. Now they added this two part, 1 plus mu divided by tan alpha multiplied by phi. This one they would like here in this modification, they consider the friction and they consider the inhomogeneous deformation. So it is the ideal deformation, y flow multiplied by ln AO divided by F. This is the ideal deformation as a simple tensile test or simple tensile problem. But now we added the phi for inhomogeneous deformation and this part to consider for friction happening in the process. It's 1 plus mu divided by tan alpha. Alpha is the angle. Can you see that? Alpha is the angle, angle, multiplied by phi. What is the phi? Phi is the inhomogeneous factor. Phi equal to, they experimentally obtain it as 0.88 plus 0.12 d divided by LC. This is a phi value. What is the d? Actually, d can be obtained as average diameter of the work, which is the do plus df, do plus df divided by 2, and LC contact length. This one contact length equal to from geometry do minus df divided by 2 sine alpha. This is D and LC. Then phi and mu have been added here to modify the equation to deal with the additional factor friction and inhomogeneous deformation. Force can be obtained as C multiplied by A final. It must be here. Again and again, I remind you, you do tensile force. So force must applied here. Then force equal to sigma multiplied by A final, right? Then A final multiplied by sigma, as here you can just simply apply. So this is the actual deformation. This is the actual deformation. Okay, let's take an example. Let's read it and understand together and try to solve it together, right? Wire is drawn through wire here, as you can see here, wire is drawn through a draw die. As you can see here, entrance angle 15 degree, alpha is 15 degrees, starting diameter 2.5 millimeter, starting final diameter 2 millimeter. Coefficient of friction here given is 0.07. Coefficient of friction mu is given 0.07. The metal has a strength coefficient K is given. Material strength coefficient cold working K is given. If the material will cause the average flow stress to be 0.83 of the final, so average flow stress will be 83% of the final flow, determines the value of strain hardening exponent. Then put the equation YF, Y bar flow equal to Y flow 0.83 Y flow. He told me like this: if the metal will cause the average flow stress will be 83% of the flow stress. Then average flow stress equal to 83% of the flow stress need a strain hardening exponent. Both this one, then this one, Y flow equal to K epsilon n divided by n plus 1 here. This is a Y bar flow, and this is a Y flow equal to K epsilon n, right? Then in very simple way, K epsilon n gives the K epsilon n then you get one equation as n, then you obtain n strain hardening exponent can be obtained n equal to 0.2. Right. Second, what is the draw stress? What is the draw stress? Means sigma drawing. What is a sigma drawing? In a very simple way, you put the equation. You put the equation. Whenever he told you what is a sigma drawing, you put the equation. You must put the equation. Equation says that sigma drawing equal to y bar flow multiplied by 1 plus mu divided by 10 alpha multiplied by phi ln AO divided by AF. AO is obtained. AF is obtained. He gave me initial and final diameter and circular shape. Then you obtain AO, you obtain AF. Then AO can be obtained. AF can be obtained, as you can see. Then done. Right. So you can also, we need to obtain phi. Phi equal to 2.88 plus 0.12 d divided by LC. We need to obtain d and LC. D equal to do plus df divided by 2. LC equal to do minus df2 sine alpha. Then you can obtain d and LC. He give me do, df, and alpha. Then you apply, get d and LC. D and LC, then you can apply here, you get phi. Phi is obtained, right? Mu is if given and alpha is given. Y flow still not, then epsilon you need to obtain Y flow, we need to get Y flow equal to K epsilon n divided by n plus 1. This Y flow, then epsilon, we don't know, epsilon ln AO divided by AF. Then AO is known, AF is known, then you get epsilon. Then you come back here, you apply, you get Y flow. Then as long as all factor is given, obtained now, then sigma D can directly apply here, you get sigma D equal to this value. Then next, what is a force? Force equal to AF. AF, I'm telling again, AF multiplied by sigma D. This sigma D in AF is in, AF is here, AF is here, we calculate, then you apply, get force. This is a force in a wire drawing. Any question? Any question, guys? Is it clear? If you have any question, you can stop me anytime, definitely. This is another example. It is another example. Let's read it together. Let's read it together. Round rod annealed. This is a material 302 stainless steel. K and N given. K is this is a constant, and this is the N with strain hardening exponent. Is being drawn with a diameter from diameter 10 to 8. We reduce from 10 millimeter to 8 millimeter at speed 0.5 meter per second. This is the speed, deformation speed. I mean, wire drawing speed. Assume that the friction, listen to me carefully here, listen carefully, assume that the friction and redundant work is inhomogeneous deformation. Assume that the redundant work, the frictional and the redundant work together consist of 40% of the ideal work. What does that mean? Means that the ideal work, the actual value, 40% higher than the ideal work. It means, this meaning, work, he said work actually. It means that, let me say, he said work means actual work should be done equal to 1.4 ideal work ideal. It means that actual work applied equal to 1.4 ideal work. Work equal to force multiplied by distance. Mechanical work equal to force multiplied by distance. Distance is same because deformation is same in ideal case. Or so deformation, then force multiplied by force multiplied by distance equal to force multiplied by distance. Then distance goes distance in remaining force. Then the actual force applied equal to ideal force plus 40% of ideal force. It means that ideal force and additional 40% to consider for friction and inhomogeneous, then total actual force is 1.4 ideal force. 1.4 ideal force. What is the ideal force? Ideal force, no friction and no homogeneous deformation. Then ideal force equal to y bar flow, which is sigma drawing multiplied by AF. Sigma drawing multiplied by AF, meaning y flow multiplied by epsilon multiplied by AF. This is the ideal case. There are no phi and no mu. Then you calculate based on that. You get y flow k epsilon n plus 1 divided, sorry, this is wrong. This is k epsilon n. This is mistake here. There are a mistake here. There are no one. Sorry. K epsilon n, just only n. K epsilon n divided by n plus 1. This is a y flow. Y bar flow equal to K epsilon n divided by n plus 1. You apply area finally, then ln AO divided by F, you get F ideal. Epsilon here can be obtained as ln AO divided by AF, right? Then you can just give F ideal. F ideal, then you multiply y.4, you get F actual. This is F actual. You can see that F actual equal to F ideal, and then additional 40% of the F ideal to consider for friction and homogeneous deformation. You get F actual. Then the power required for operation equal to F actual multiplied by V, which is the speed of the operation. Speed of the operation. Clear? Is it okay? Understood? Any question? Right. Next is whatever we call a tube drawing. Tube drawing. We still talk about the wire drawing. Next is the tube drawing. Tube means hollow. Hollow inside. There are no solid. It is not closed. Solid cross section. It is a hollow. This whatever we call tube drawing. Here, this is a tube. Actually, in case of tube drawing, you cannot just simply make drawing unless you put whatever we call mandrel inside. This is a mandrel inside. The mandrel is very important. Why very important? Because mandrel actually maintains the internal to not collapse, internal dimension to not collapse. Otherwise, internal dimension here will be destroyed, will be collapsed. You cannot draw hollow tube unless you put a mandrel inside to maintain the internal dimensions. This one we call a stationary mandrel. This one we call a stationary mandrel. This one we call stationary mean ثابت يعني بالعربي ثابت mandrel ثابت وبنحطه هنا ونسحب then pull the wire or tube, sorry, we pull tube, then here's it can maintain the dimensions. This is floating. Floating mean no fixed. It's floating. So what you put here, and the friction inside here will bring this one to the correct position. This one we call it floating, and this one we call it is a moving mandrel. Moving mandrel, we pull it together with the this is a die. We pull it together with a tube. This is a tube. We pull both together and moving together. We call it is a moving mandrel. Okay, let me show you a nice video. Help you to understand more about this one. Just give me a second. Right. It's coming. It's coming. Just a second. Already. Here, this is a die. This is a die, drawing die. Then he make cross section to show you. This is the die. Can you see that? This is the die here to reduce the wire or tube, definitely tube. This is a tube, but this is the internal dimension here. Can you see? This is the internal. When you draw, you destroy unless you put the mandrel. This is the mandrel here. You bring the mandrel here, and the other mandrel is smaller one. This is bigger one, smaller one, and then you start, to fix. Sometimes it movable to fix. This one is smaller than this one, and then you just move. You start pulling this one here, and this one will stop here in certain area to maintain the dimension. Then you pull it to maintain the dimension at certain. So mandrel here, this is a mandrel. Actually, let me tell you that the easy way, in many cases, the easy way to do is to put sand inside. The easy way to do actually, in many cases, the easy way to do actually put sand inside and put sand here will working like mandrel. movable, variable diameter. It can maintain the internal dimension and easy way to do this one. Some cases you do. Sometimes some cases use mandrel. Some cases in a small companies they use sand inside or something. This is whatever we call is a tube drawing, right? So this is the end of chapter 15. This is the end of wire and bar drawing, and this is the end of chapter 15. Any question generally? Generally, any question? Okay. Yes, Muhammad.
Doctor,
I'm
if you
listening.
have a question outside the lecture, do you ask now or at the end of the class?
خليها في نهاية الكلاس يا محمد، يعني خلينا نخلص. أنا دلوقتي السؤال خليه ريليتد للكلاس، هخلص ونتكلم زي ما أنتوا عايزين. I will be here يعني
Okay.
discuss together
تمام.
as you wish.
Okay.
It's okay. If no questions, then let's start. If no question, meaning let's start to next is chapter 16. Then now all done, almost all done, as you can see here. Still only remaining chapter 16, which is a sheet metal working chapter. This is the last chapter here in this subject this semester. So chapter 16, sheet metal work. Let's just give some introduction about sheet metal working and continue discussion about sheet metal working inshallah next time. Chapter 16, sheet metal working, chapter 16, we talk about 16.1, 16.2, 16.4, and 16. This is the items that we're going to cover. 16.1, 2, and 4, and 5. We're going to cover cutting operation, bending operation, other sheet metal forming operation, and die press and sheet metal process. This is the items that 4 items that we're going to cover in this chapter. Okay, sheet metal forming process. Right. Sheet metal forming. We have whatever called sheet and plate. Sheet and plate. Usually, sheet is work thickness less than 6 millimeters. So we talk about whatever is sheet is less than 6 millimeters. This is a sheet initially rolling. We do rolling previously. Now we talk about sheet, right? How the sheet is obtained, how the sheet is prepared. It is prepared by rolling. So initially, rolling, rolling is a bulk metal deformation. This is the initial step. So we do rolling. Initially, we do rolling and prepare the sheet. So sheet is prepared by rolling. So we bring sheet. And now we're going to deal with the sheet here. In this chapter, we use the sheet to do deformation of the sheet. Usually less than 6 millimeter. And here we can do metal deformation, like as you can see here, this sheet we can use to make deformation like bending, like drawing, like whatever process we do in a sheet. So initially sheet like this, and here we do deformation to deform it with different shape. This is a sheet metal processing, right? In a sheet metal deformation, we avoid to do any deformation. I mean any other processes in the sheet. So bring sheet and directly we do deformation in the sheet. We don't try to make tensile, we don't make compressive, but simply we do deformation like whatever bending, whatever drawing or cutting. So this usually is done on the sheet. Factor influencing the sheet metal forming is the elongation. Definitely, this is the material itself. This factor is related to the material that the sheet made of. So aluminium, for example, sheet made of aluminium, sheet made of steel. You can see different properties like elongation, yield point elongation, azeotropy, grain size, residual stress, spring back, wrinkling, or coated sheet or whatever. This is the process of the sheet which is done previously before it come. Whether this sheet have a residual stress or not, whether this sheet annealed or not, what is the grain size that been or is grain size of the sheet from the previous deformation, I mean, which is rolling. Is there annealing, recrystallization, or there are residual stress? All this information must be provided so you know what is this deformation before you dealing with this one to do more deformation as a sheet metal deformation on the sheet, right? Advantage of the sheet metal forming is this is mainly, if I said sheet metal forming, listen to me carefully. Sheet metal forming is mainly cold working, right? Mainly cold working. What does that mean? It means that the benefit or advantages of sheet metal working is advantage of the cold working. We know that there are advantages of cold working over hot working or warm working. So what is this advantages? You know that the structure of the material will be deformed. You get this, you get grain size deformation. I mean the grain, you get grain distortion, grain deformation leading to high strength because of strain hardening exponent happen. Good dimensional accuracy as a cold working, no heating and no cooling. Then you get good dimensional accuracy, good surface finish, relatively low cost because no additional heating compared with the hot and warm economical mass production. All this is the benefits actually not for sheet metal working but also for cold metal working as well. And sheet usually is cold metal work. That's why they said this is the advantage of sheet metal working because mainly it is cold working. Sheet metal terminology being used in sheet metal working, which is a bunch and die. Bunch, this is a tool. This is a tool being used in metal working. This is a bunch and this is a die. Always this terminology being used here. Bunch and die. A stamp press is a machine. Stamping press, we call it, is a stamping press is a machine to be used to make sheet metal working, and stamping is the material, is the work part, which is a sheet. Sheet, we call it as stampings. The items that we're going to cover here: cutting, bending, and drawing. This is a sheet metal working. Cutting here to cut, separate this sheet to twice. Someone said that you told us here this is the deformation and no cutting. Yes, I agree with you. So why you said cutting here? Actually, this cutting will not cut to shape, but we cut to prepare the sheet for the deformation. Actually, for example, let me tell you, initially we have the sheet with this side. This one come from rolling. So this is a sheet. But I don't want to have this size. I need to cut this sheet like this to be used in metal forming. So for example, I need to do this cut. I need to do this cut. Then I need to do this cut. Then probably I need to do this cut. Make it twice. So this one time, this one time. I need different size. I don't want, I cannot use a sheet that came from the metal forming with the original size, but I need to do different sizes being used in other process. So cutting here is to bring the sheet, to cut the sheet with the correct size or with the needed size for the next operation. So this is the meaning by cutting. So shearing here, we cut, meaning this is a part we cut here, this is a punch, and this is a die. We cut here to separate, to make it ready for the next one. Shearing to separate large, this is a larger sheet, make it smaller. So we have planking and the punching, we will discuss in detail. Bending here, this is a bending to deform, to make this kind of deformation. Drawing is to create a concave shape in a part, as you can see here. This is a punch to draw the material to create this one. This is a several process in sheet metal work. Start with 16.1. 16.1 is the cutting, sheet metal cutting. So first section we're going to discuss about is the cutting. Cutting is to cut the part of the material, as I told you. Actually, time is finished. I think I have to stop here and continue next time discussing about the sheet metal forming in a cutting. I will stop recording.